I'm a professional mathematician and we're going to master epsilon-delta proofs together. We're going to do 5 epsilon-delta proofs in this video and each one's going to get in increasing difficulty and I'm going to show you how to think about them like a mathematician. So we have the first one, which is limit x goes to 3 of 5x minus 9. The first thing before we prove what this limit is to actually calculate it. So here we just plug in x equals 3, it's a continuous function. So we get 15 minus 9, which is equal to 6. So we need to rigorously prove that it's equal to 6. So what I just said is not a rigorous proof, and we're going to do the epsilon-delta definition. Now what does that really mean? Well, what this limit is saying is as x approaches 3, 5x minus 9 approaches 6. So we want to make the absolute value of 5x minus 9 minus 6, we want to make this small as the absolute value of x minus 3 becomes small. The absolute value of x minus 3 is the distance from x to 3. And this is the distance from 5x minus 9 to 6. So another way of saying it, which is the epsilon-delta formulation, is that no matter how small, it's a game we are playing, no matter how small I want to make this number, right? I want to make it less than epsilon. You will tell me how close x has got to be to 3 in order for this to be less than epsilon, for this distance between 5x minus 9 and 6 to be less than epsilon. So you're going to pick a delta. So that absolute value x minus 3 less than delta implies that the absolute value of 5x minus 9 minus 6 is less than epsilon. Another way of saying that is that for each epsilon greater than 0, for each degree of closeness from 5x minus 9 to 6 that I choose, you can find a degree of closeness from x to 3 that ensures that as long as this degree of closeness from x to 3 is satisfied, absolute value x minus 3 is less than delta, this is going to be satisfied. 5x minus 9 minus 6 is going to be sufficiently small. So your delta we want to find is going to be solved in terms of epsilon. Okay, so we want to pick a delta in terms of epsilon because as epsilon gets smaller, we need delta to also be smaller. So delta is a function of epsilon, and we're going to basically start off by manipulating this expression and finding what delta should be and then writing our rigorous proof. That's how epsilon-delta proofs are done. You first figure out what delta should be and then you write the proof. You backtrack before the proof. So here we're going to say, okay, the absolute value of 5x minus 9 minus 6 is the absolute value of 5x minus 15, okay? And we want to make this small, knowing that absolute value x minus 3 is small, okay? We want to figure out how small this has got to be, so this is small. So we need to express this in terms of absolute value x minus 3. That's going to be the general philosophy. So we can write this as 5 times the absolute value of x minus 3. That was nice enough that we could express this as 5 times the absolute value x minus 3. So what does delta have got to be so that this is less than epsilon? How do we ensure this is less than epsilon? Well, as long as absolute value x minus 3 is less than epsilon over 5, right? If we take delta equals to epsilon over 5, then 5 times absolute value x minus 3 will be less than epsilon. So that's going to be the principle, and now we write the rigorous proof. So this is all there is to it, okay? Take some time to get used to it, but that's all there is to it. And the rigorous proof looks as follows. We simply say that let epsilon greater than 0 be arbitrary, okay? So I'm going to be very precise. You can actually do this as a blueprint for all of these proofs. Let epsilon greater than 0 be arbitrary. That's the degree of closeness. That's saying how close do I want this quantity? How close do I want 5x minus 9 to be to 6, okay? And that's my epsilon. So the epsilon greater than 0 will be arbitrary. So what we're going to do is going to say that if delta is equal to epsilon over 5, so if absolute value x minus 3 is less than delta, then this is going to be less than epsilon. So how the proof's going to go is if delta is equal to epsilon over 5, then absolute value x minus 3 less than delta implies that, what does it imply? It implies the absolute value of x minus 3 is less than epsilon over 5, which implies that 5 times the absolute value of x minus 3 is less than epsilon, which finally implies that the absolute value of 5x minus 15 is less than epsilon. So no matter what epsilon we picked, okay, and 5x minus 15 is very important to write it as the absolute value of 5x minus 9 minus 6. Okay, that's going to be less than epsilon. So no matter how close I wanted 5x minus 9 minus to be to 6, I could ensure that if delta was that epsilon over 5, then as long as x was that close to 3, then 5x minus 9 would be that close to 6. Okay, so just repeated myself a lot here, but I want to drill in the concept. Okay, We're just trying to solve for delta in terms of epsilon in each of these proofs. And we've done that, and then once we've done that, we need to write out the proof in this way to start off with epsilon greater than 0 being arbitrary. Let's get on to the next one now, okay? So the next one is going to be quite more interesting, okay? So let's get into it. All right, so the next epsilon delta proof we're going to do is this limit, which is now a quadratic polynomial. So it's going to get a whole lot more interesting and subtle, but don't worry, we're going to go through it very simply. So you have limit x goes to 5 of x squared minus 2x minus 10. So first step is what the limit should be. What should it be before we prove that it is that? So if we plug in x equals 5, again, it's a continuous function. So you have 25 minus 2 times 5, which is 10. So 25 minus 10, which is just 5. So that's going to be our limit. And now we just need to prove that that is correct. So again, we want to make the absolute value, so I'm going to write this out. We want to make the absolute value of x squared minus 2x minus 10 minus 5. We want to make this small given that the absolute value of x minus 5 is small. Okay, so I'm phrasing this in a number of ways to just intuitively connect it to the epsilon delta proof. So in other words, we play a game. If I want this to be less than epsilon, okay, if I want this distance to be small, in other words, this x squared minus 2x minus 10 to approach 5, you're going to tell me a delta so that as long as the absolute value of x minus 5 is less than delta, I can guarantee that my x squared minus 2x minus 10 will be that close to 5. Okay, so how do I find that delta in terms of epsilon, or how do you find that delta in terms of epsilon? What you need to do is you need to write this expression somehow in terms of x minus 5. So this is the preliminary steps, okay? It's not the actual proof that will come later on that side of the board. The preliminary steps, I'm not saying that right. The preliminary steps is we need to write this in terms of x minus 5. So this is going to make sense, okay? This is just going to come to factoring our quadratic. So you're going to have the absolute value of x squared minus 2x minus 15, okay? So that's going to be our quantity. And of course, we know this has a 0. By definition, by sort of the way the intuition is going, when x is 5, this is 0, right? Because we want to show when x approaches 5, this approaches 0, but we know when x is exactly 5, this is 0. So this is going to factor, okay? So we can factor a quadratic, using the middle term or the quadratic formula. It's x squared minus 5x plus 3x minus 15, and then you can do the factoring. I'm just going to do it in one step. It's going to be x minus 5 times x plus 3. Okay, and one quick check is just to plug in x equals 5 and x equals negative 3 and check that you get 0 for this. Okay, so x equals negative 3, you get 9 plus 6 minus 15. So it's 0. So you've got that. We want this to be less than epsilon. Now, this is a little trickier because it's not a constant now that we're multiplying the absolute value of x minus 5 by, right? So we're multiplying it by x plus 3, and that's a function of x. So how are we going to handle this? So before I get into the proof, I'm just going to tell you the intuition first of all. And the intuition is pretty nice. It's pretty cool. Basically, we have the absolute value of x minus 5 times the absolute value of x plus 3, okay? And that we want that to be less than epsilon. So what should we take delta to be? Now here's a fallacy, okay? I'm going to tell this to you as a fallacy. We cannot take delta to equal to epsilon divided by the absolute value of x plus 3. Okay, this is actually wrong. Why can't we take delta to be that? Well, delta should be dependent only on epsilon. Okay, so it cannot be dependent on x. Okay, there are a lot of different quantifiers in this. There is the x, there is the epsilon, there is the delta. We have to make sure our delta is only dependent on epsilon. Once I've specified how close we want this expression to be to 5, which is by our epsilon, you need to tell me a delta that is independent or dependent only on epsilon but independent of x. So as long as the absolute value of x minus 5 is less than delta, we have this expression. So how are we going to find our delta? Well, basically, we're going to have to be a bit clever here, okay? And this is the trick we're going to use. When x is exactly 5, our x plus 3 is going to be 8, okay? So our first guess is to take delta equals to epsilon over 8. The problem with this is that it doesn't universally work, because remember, when x is close to 5, x can be either to the right of 5 or to the left of 5 on the number line. So if we imagine a range, I'm just going to be very specific here. Imagine a range from 4 to 6. Then our x plus 3, when x is equal to 6, our x plus 3 is going to be 9. So as our x approaches 6, our delta should be epsilon over 9 to ensure that if the absolute value of x minus 5 is less than delta, but also x is close to 6. Okay, let's say we don't know anything about delta. Delta could be large. But when x is close to 6, then our x plus 3 is going to be close to 9. So our delta should be epsilon over 9 there. But as our x gets close to 4, our x plus 3 is going to get close to 7. So our delta will be epsilon over 7 here. Okay, so we need our delta to be small enough. That's our luxury, that we can ensure our delta is as small as we like. We can pick a delta, it can be as small as necessary as long as we ensure that this quantity is less than epsilon. And so what we're going to do is we're going to pick the smallest of the two values. Okay, if delta is epsilon over 9, that's going to take care of any x in this range from 4 to 6, right? So if x is within 4 to 6, which we can ensure because we can make delta as small as possible. So first step, I'm going to say, or you're going to tell me, the delta is going to be less than 1. Okay, we're going to make delta less than 1 by default. Doesn't matter what epsilon is. Epsilon could be 100. Make delta less than 1, fine. And then on top of that, you want to make delta less than epsilon over 9. Okay, so that takes care of, as epsilon gets really, really small, then delta should be less than epsilon over 9 because you're going to wiggle to the left or to the right of 5. So I hope that makes sense, but I'm actually going to write the proof now. Okay, so you're going to see it in action, which hopefully will clarify things. We're not going to take epsilon over 8. We're going to take delta equals to epsilon over 9. And you're going to see this work in action, okay, when you write out the epsilon delta proof. So let me erase this and write out the epsilon delta proof right now. All right, so let's write it out. So our proof is, let epsilon greater than 0 be arbitrary. Okay, let epsilon greater than 0 be arbitrary. And we want to ensure, so our choice, you know, when I said 4 to 6, that was not special. I could have gone 3 to 7 as well. Okay, and then I would have said delta should be less than 2, okay, because within 2 or 5, and delta should be then less than epsilon over 10. Okay, that's what I would have done. But let me write the proof out. Okay, so let epsilon greater than 0 be arbitrary. Let delta equal to, and here's going to be the way we'll express this, the minimum of 1 and epsilon over 9. Okay, so it is going to be the smallest number among 1 and epsilon over 9, whatever that is. So by definition, it's going to be less than 1, or less than or equal to 1, and it's going to be less than or equal to epsilon over 9. Okay, so it's definitely less than or equal to 1. Okay, so we're going to be in this range of 4 to 6, which we're allowed to do. We can choose any delta as long as it serves our purpose. Okay, now we have that if the absolute value of x minus 5 is less than delta, then we know for a fact that the absolute value of x squared minus 2x minus 10 minus 5, and I'm writing this slightly differently from last time. We want to make this quantity small. Okay, so I'm going to now simplify it to something in terms of absolute value x minus 5. You can do it either way, or you could just write out in the other direction. So I'll explain that. You can write out x minus 5 times x plus 3 is going to be less than this, and then backtrack to this quantity. We can do it either way. But we're going to do it this way. Then this quantity is going to be the absolute value of x minus 5 times x plus 3, which we know, right? We know that because we've just factored the quadratic like we did. Okay, this is now our proof. So we factored the quadratic, and we know that because the absolute value of x minus 5 is less than delta, okay, so we know that delta is the minimum of 1 and epsilon over 9. We know for a start that the absolute value of x minus 5 is less than epsilon over 9, right? Because delta is the smaller out of 1 and epsilon over 9. So it's going to be less than epsilon over 9 times the absolute value of x plus 3. But now here's the deal. X plus 3, right? Because delta is the minimum of 1 and epsilon over 9, so we have the 1 as well. We know that x is between 4 and 6. So the maximum value of x plus 3 is going to be 9, right? Because x is between 4 and 6. It's not going to quite hit 9, okay? But because x is, absolute value x minus 5 is less than delta. But therefore, we know the absolute value of x plus 9 is going to be less than 9 because x is less than 6. And so that means that this is going to be equal to epsilon. Okay, so we've got a strict inequality here. So we've ensured that, you know, whatever epsilon I've chosen, you found a delta, which is the minimum of 1 and epsilon over 9, to ensure that if the absolute value of x minus 5 is less than delta, then the absolute value of this expression x squared minus 2x minus 10 minus 5 is less than epsilon. So we've ensured that no matter how close I want x squared minus 2x minus 10 to be to 5, you can find a certain degree of closeness of x to 5, because we have the limit as x goes to 5. You can find a delta, playing a game so that if absolute value x minus 5 less than delta, then absolute value x squared minus 2x minus 10 minus 5 is less than epsilon. Okay, and I hope that makes sense. And I want to make one point is we could have, our 1 was arbitrary. Okay, so this helps sometimes. If you're studying this, you may wonder, why did I pick 1? Well, if I picked 2, that would have also been fine. But if I picked 2, I would have had to make this epsilon over 10. Because then if I picked 2, all we knew is that x would have been between 3 and 7. And then when x is 7, we know that our x plus 3 is going to be 10. So we need our x minus 5 to be less than epsilon over 10 here. Here we'd only need it to be less than epsilon over 6, but our worst case scenario is to absolutely ensure, in this case we need it to be much smaller. So we just pick epsilon over 10 as delta, and then we would say min 2 comma epsilon over 10. Okay, and I want you to drop a comment down below. Okay, just as a practice, what if I said min 0.5? What if instead of 1 I said 0.5? What could I choose this epsilon over 9 to be? Okay, what are some options I could choose so that it would ensure that if the absolute value of x minus 5 is less than delta, then the absolute value of x squared minus 2x minus 10 minus 5 is less than epsilon. Okay, so that's an exercise to you. Now we're going to get to the next one. So I've got 3 more, and I hope you're loving this video. Please don't forget to leave a like and subscribe if you're enjoying my content. It makes a huge difference to my channel. And if you're really enjoying my content, please consider subscribing on Patreon. Okay, it makes a huge difference. I do everything on my own, and I'm trying to build this channel to create elite, infinite, free, accessible math education at all levels for everyone. And I'm deeply grateful to everyone who supported on Patreon, Alex and Nathan, for their ongoing support. Thank you so much. I hope you're watching this video, and if you're considering supporting, just check out my page. It makes a big difference for me, and I'm super grateful. I deeply value everyone who subscribes and everyone in general. Okay, it doesn't matter, even if you choose not to subscribe, deeply value the fact that you're watching, and I hope I'm delivering a lot of value of content to you. It's all free content, and I'm so happy I'm able to do it to help as many people as possible. That's my ultimate goal, to change lives through math education and create a repository of advanced math across everything that currently doesn't really exist. There's basic math, there's some advanced math, but nothing with everything, and that's what I'm trying to do with this channel. So let's get into the next one now, which is going to be another fun epsilon delta argument. Alright, so here's our next epsilon delta proof. It's going to be limit x goes to 3 of x plus 2 over x plus 7. I'm giving you a representative sample. Okay, most of the problems you encounter are going to be kind of like the 5 we're going to talk in this video. So we've got this example, and what I want you to do is actually try it yourself. Okay, try to play around with it yourself, and then watch the video just to sort of confirm and see how we're both thinking about it, so you can really consolidate your understanding. So try to sort of work along. The first step, every time I'm going to do the same methodology. The first step is when x approaches 3, when x is exactly 3, you get 5 over 10. Okay, so we're going to get a half. Okay, 5 over 10 is a half. This is a continuous function. Now I just want to make a comment is, suppose you were trying to do an epsilon delta proof where it was an indeterminate form. Okay, like 0 over 0. Usually with those examples, what you do is you simplify the function. So as an example, I could sort of write this down. If you had something like limit x goes to 1 of x squared minus 1 by x minus 1, right? Then you couldn't actually plug in your x equals 1, right? You wouldn't get an expression. You'd get 0 over 0 if you plugged in x equals 1. But the same principles would apply. You basically want to, that this quantity, when you deal with these, this quantity is just equal to x plus 1 when x is not equal to 1. Okay, so as long as x is not equal to 1, then this quantity is x plus 1. And so then you can basically do the same argument as if you had x plus 1, because they are the same expression. And that's how you do limits when they're 0 over 0 forms. If you're not using L'Hopital's rule, if you're using that, then already you've gone through all the work with epsilon delta secretly. But in this case, if you're just simplifying, this expression is true. And a quick point, and I'm not saying this in these videos or in this video at all, because when you're doing epsilon delta proof, you can just say that if absolute value x minus 1 is less than delta and x is not equal to 1. Okay, so I haven't included that, but to be very rigorous, I should include that, because limits don't consider the value of the function at that point. Okay, so in our epsilon delta proof, we only need to ensure that if x is not equal to 1, and then absolute value x minus 1 less than delta, then our expression that we want, which in this case is x squared minus 1 by x minus 1, we want to ensure that is less than epsilon. Okay, so we want to find a delta in terms of epsilon, but we don't need to consider the case x equals 1. But in our proofs, they're all correct, because I've also said it's true for x equals 1, and that's stronger. Okay, so that's continuity of the function. But anyway, let's now get into this limit. So I'm just going to erase this. All right, so let's get into this limit now. So basically what we want to do, it's the same game. We want this expression x plus 2 divided by x plus 7. Absolute value is a distance as usual. So we want this minus a half to be less than epsilon. Okay, so we want to ensure that this expression is less than epsilon as long as x is sufficiently close to 3. Okay, so how close to 3, that's what we have to find out. We want to say that for each epsilon I pick, if I want x plus 2 over x plus 7 minus half to be that small, the absolute value to be that small that it's less than epsilon, then you're going to tell me a delta. So as long as x minus 3's absolute value is less than delta, i.e. x is sufficiently close to 3, then x plus 2 over x plus 7 is sufficiently close to half. So we want to find delta in terms of epsilon. It's the same game. So again, as always, we simplify the expression here and try to write it in terms of x minus 3. Okay, so we try to write it in terms of x minus 3. Well, let's just get into it. So here we have x plus 2. Just make a common denominator. That's what I do. So x plus 2 multiplied by 2. So we get 2 times x plus 2 divided by x plus 7 minus x plus 7 divided by 2 times x plus 7. Okay, so I should say 2 times x plus 7 and 2 times x plus 7 here. And I want this to be less than epsilon. Okay, so that's my expression. And so in this situation, I just simplify what's inside this absolute value. So I'm going to do it on this side of the board now. So we're just going to get 2x plus 4 minus x plus 7, which is going to be the absolute value of x minus 3 divided by 2 times x plus 7. Okay, so that's going to be our expression, and we want to say that this is less than epsilon. Okay, now we see the absolute value x minus 3, which you should see. Okay, we know this expression should be 0 when x is 3. Okay, that's because we're dealing with a continuous function that is defined at 3, and the value at 3 is the limit as x goes to 3. So that's what we intuitively know. We're creating a proof based on our intuition. So now we know that we're going to see an x minus 3 if we simplify it right. We've seen that. Now we need to pick our delta. So how are we going to do that? Well, again, okay, so we have this extra expression like we did last time. So we can separate this into 2 pieces. Okay, we have our absolute value x minus 3, and then we have our 1 over 2 times x plus 7. Okay, again in absolute value, we want this to be less than epsilon. Now, again, it helps. It's not rigorously true, but it helps to say that if x minus 3, okay, if absolute value x minus 3 is going to be less than epsilon times the absolute value of 2 times x plus 7, okay, if this is true, if we know that, then we can ensure that this quantity is going to be less than epsilon, right? So if we take delta to be this, then we've solved the problem, but we can't do that because this is dependent on x, and we want delta to be only dependent on epsilon. So how do we pick our delta? So again, we think about the extremes, okay? So we pick what is x plus 7 going to be when x is 3. When x is 3, x plus 7 is going to be 10, and this is going to be 2 times 10, which is 20, okay? But then, of course, we know that, we want our delta to be equal to epsilon times 20, okay? That's actually like a different sense as earlier. It's not epsilon over something, it's 20 epsilon. But that's not enough, because now if x is, within some units of 3, right? So for example, if you have 3 on the number line, and I can even write it here. If you have 3 on the number line, and your x is going to be like, say, between 2 and 4. It doesn't matter what I pick. I'm just picking 2 and 4. It does matter as long as the denominator is non-zero. Okay, so I have to pick it in the domain, some interval in the domain. But if I say that x is between 2 and 4, then when x is exactly 4, I want my absolute value x minus 3. When x is approaching 4, I want my 2x plus 7 to be, it's going to be 22, right? 22. So our delta needs to only be 22 epsilon. But when our x is approaching 2, our 2x plus 7 is going to be 2 times 9, which is 18. Okay, so we're going to get an 18 epsilon here. So remember, we want to pick the delta that's optimal no matter what situation we have. Okay, so at 3 exactly, we have 20 epsilon. So the safest thing to do is to pick delta to be the minimum of 1, okay, because I've looked at the range from 2 to 4, and 18 epsilon. And then no matter what x is in this range, 18 epsilon is going to take care of everything in this range, because all the other required deltas or required values of the 2x plus 7 in that range are going to be higher, okay, than when it's at exactly 2. Okay, so again, I'll write out the proof. I hope that everything is so far very clear. I'll write out the proof now, and really make that precise. So let's do that. All right, so let's write out the proof. So how these proofs go is always the same. Let epsilon greater than 0 be arbitrary, so it doesn't matter what epsilon is. Our goal is to pick a delta so that if the absolute value of x minus 3 is less than delta, then the absolute value of x plus 2 over x plus 7 minus half is less than epsilon. So let's just get into it. It's super fun. So let delta equal to the minimum. So I'm going to write this again. Let delta equal to the minimum of 1 comma, in this case 1 comma 18 epsilon. Okay, so actually you could just say, and this is another point in these proofs, you know, you don't have to pick the optimal delta. Okay, you can say let delta be the minimum of 1 comma epsilon. That would be even better. Okay, that would make it easier. That's fine. But the main thing is it's nice, you know, it's just like an aesthetics, like an artistic thing. It's like people like to do it this way, but you don't have to. As long as you say the end expression is less than epsilon that you want, it doesn't matter what delta you pick. Okay, so if we know it's less than epsilon over 18, then that's also less than epsilon. So that's totally fine. The only thing we want to be careful about, and I'm just saying this before I get into the proof, is we don't want to in the end say it's less than some expression in epsilon that is not less than epsilon. We don't want our proof to read as if absolute value x minus 3 is less than delta, then this expression, the absolute value of this expression is less than say 5 epsilon squared plus 7 epsilon plus 2 or something, or 5 epsilon squared plus 7 epsilon. Now, technically, I'll talk about this a bit more, but technically that expression, if we can say it's less than 5 epsilon squared plus 7 epsilon, that's technically okay because that expression tends to 0 as epsilon tends to 0. Okay, so, but it's important that we, you know, to be very rigorous, we want our end expression to be less than epsilon because we're saying that's our exact degree of specificity and we're making it within that range. Okay, if we say it's 5 epsilon squared plus 7 epsilon, advanced math papers, they do that. Okay, and that's fine. You know, they can say it's some constant times epsilon, and that's fine. That solves the problem. They don't bother to go and say let delta be whatever it was divided by that constant. Okay, but we are just being very precise because this is like the first steps in these proofs to make sure our rigor is correct. So anyway, let's get into this. So let delta equal to this minimum of 1 and 18 epsilon, and now what we can do is we can say, all right, so if the absolute value of x minus 3 is less than delta, then we know, and I'm going to do it slightly differently as I did earlier. I'm going to say, then we know that the absolute value, so whatever expression we had earlier, the absolute value of x plus 2 divided by x plus 7 minus half, what's that going to be? That's going to equal to, after all our simplifications, that was x minus 3 divided by 2 times x plus 7. Okay, so we know that this is going to be less than, well, delta was the minimum of 1 and 18 epsilon. Okay, so it's the smaller of the two, whatever that is. Okay, so it's less than or equal to both of them. So because it's less than 18 epsilon, we can say the absolute value of x minus 3 is less than 18 epsilon, and then divided by 2 times the absolute value of x plus 7. Absolute value of 2 is 2, so I just took that out. Okay, it doesn't really matter. But now the point is that because delta is a minimum of 1 and 18 epsilon, so using the 1, we know that the 2x plus 7, x plus 7 is going to be the smallest value x plus 7 could be, right? Because x is within 1 of 3, okay? Because delta was a minimum of 1 and 18 epsilon. So the smallest value that x plus 2 times x plus 7 could be is actually 18, okay? Because if x is 2, right? X is within 1 of 3, so if x is 2, then we get 2 plus 7 is 9, 9 times 2 is 18. Okay, so this is going to, the denominator is greater than 18, so that means if you take the reciprocal, you get a less than sign. It's going to be less than 18 epsilon by 18, which is going to equal to epsilon. Okay, so we've chosen our arbitrary epsilon, we found a delta, which is a minimum of 1 and 18 epsilon, and notice we've been very careful to say a minimum of 1 and 18 epsilon. Okay, so you know, we've used both the fact it's smaller than or equal to 1 and smaller than or equal to 18 epsilon, and again, you could have chosen it to be the minimum of 2 comma, then you'd have to say it was 16 epsilon. Okay, so if it was 2, then x could be 1, and then you'd have 16 as the minimum value of 2 times x plus 7 in the range of 1 to 5. Okay, so if you took the minimum of 2, then your x would be in the range of 1 to 5. Okay, so that's there. So let's, now that we've done that, please feel free to drop any questions or comments down below. I love reading comments. I do my best to reply to everyone, and I really value everyone who watches and you know, enjoys my videos and learns from them. It means so much to me. So we're now going to get to the next limit now, and this is going to be another one which is really, really fun, It's going to keep practicing with this idea that we've already seen a couple of times. But then the final limit, that's going to be slightly different, okay? So I'm just training you to think in all different kinds of situations, but I'm also showing you that it's the same scenario each time essentially. It's just the numbers and variables are changed. All right, so the next epsilon delta proof we're going to do, this is going to be really fun. It's going to be a slight variation on the previous concepts, but it really helps to drill them down. Limit x goes to -1 of x cubed plus 1. Okay, this is the second last one we're going to do, and then one more, and after this you're going to master epsilon delta proofs. You're going to know how to deal with them. They're more advanced examples, of course, but this is going to give you that foundation. So we've got this. Now the first thing to do is just plug in x equals -1. So if x equals -1, we get -1 cubed plus 1. Okay, which is going to be equal to 0. So we know that this is going to be 0. Again, this is a continuous function, so we have that luxury. We can guess the limit by just plugging in. We can exactly validate the limit by just plugging in. Now what we want to do is we want to do our epsilon delta proof. So we want now our x cubed plus 1 minus 0. Okay, the absolute value of this minus 0 to be less than epsilon. And now we don't need the minus 0 because the limit is 0. We can just put it as a single absolute value of x cubed plus 1 is going to be less than epsilon. Okay, I just wanted to show you that step, okay, just to be very clear. So we want this to be less than epsilon as long as we can find a delta. So we want to find a delta so that x minus of -1. Okay, so again, I'll be clear on this step. We can write x minus of -1 is less than delta should imply this. So if I have an epsilon and I want absolute value x cubed plus 1 to be less than epsilon. Okay, so I want x cubed plus 1 to be sufficiently small. Okay, another way of writing this, which is helpful visually, is within this interval minus epsilon comma plus epsilon. Okay, in the number line, this open interval. If I want my x cubed plus 1 to be in that range on the number line, okay, so if I want it to be, this is minus epsilon, this is plus epsilon, this is 0. If I want to ensure that our x cubed plus 1 is somewhere in this range, I need to ensure, okay, this is just going to be x plus 1. Okay, so I need to ensure that x is within some range of -1 on the number line. So I need to figure out what range that should be. So that, or we need to figure it out so that if x is within delta of -1, okay, so -1 minus delta, -1 plus delta, as long as x is somewhere in this range, we can ensure our x cubed plus 1 is going to be somewhere in this range. Okay, so we can ensure that as long as our x is sufficiently close to -1, our x cubed plus 1 is sufficiently close to 0. So we need to solve for delta in terms of epsilon. So again, the same principles apply. We need to write our x cubed plus 1 in terms of x plus 1. And again, that's going to be a factoring problem. Okay, so we're going to have to do the following. We want to say, how do we express x cubed plus 1 in terms of x plus 1? We know that x plus 1 is going to divide x cubed plus 1 because -1 is a root of x cubed plus 1. That's sort of engineered into the situation because plugging in -1 gives 0. Then we need to do that. So that's just the difference of cubes formula. So here we're going to get x cubed minus of -1 cubed. Okay, so that's how I think about it. Just use some simple formula. Factoring cubics is hard unless you have something like a difference of cubes formula or you know a root off the top of your head. So here we have x cubed minus of -1 cubed, which is just going to be the absolute value of x plus 1 times, and then we're going to get x squared minus x plus 1. Okay, so that's going to be our expression. That should be less than epsilon. Okay, so that's how we factor our cubic. Now what we can do is we can just try to do the same principles. Okay, so we want to ensure, we know that we can make sure that x plus 1 is sufficiently small. So then we need to show how small this has got to be so that this whole expression is less than epsilon. And so then we think, okay, our delta, if we say that, let's ensure that our absolute value x plus 1 is less than, and this is not part of the proof, this is just my, as always, I'm just emphasizing it's a mental thinking. We want this to be less than epsilon divided by the absolute value of x squared minus x plus 1. Okay, because then we can ensure this quantity is less than epsilon, but again, we don't have the luxury of knowing that x squared minus x plus 1 is dependent on x. We want our delta to be only dependent on epsilon, so we need to then make this precise. We need to look at x squared minus x plus 1. Again, pick an interval, okay? It doesn't matter. Pick an interval around, x equals to -1, okay? So I can draw this here. As we said, we have an interval from -1. Doesn't matter what it is, okay? So let's just pick something like -2 to 0. Okay, so we know that delta can be as small as we like. Okay, so let's assume that it's between -2 and 0, and in that case, understand what is the worst case scenario. How large can x squared minus x plus 1 be? Okay, so that's going to be the smallest possible delta that we'll need in that interval. Once we know how large the denominator is, we know how small the whole expression is, and that smallest possible value of the whole expression is what we should take our delta to be to ensure that we independent of x. Okay, so what is our maximum value of x squared minus x plus 1 on this interval? So there are a number of ways of doing this. This is calculus, okay? So this is the cool thing about this problem. We're going to secretly do all these calculus ideas, even though this is supposed to be pre-calculus in some sense. Not in the sense of depth or difficulty, but in the sense of we're establishing elementary limits rigorously, right? But we use calculus ideas, or you can complete the square, okay? You can also do that. So let me just kind of erase this 1 second. All right, so we can complete the square, or we can just use calculus. I just prefer to use calculus, if you like completing the square, you can do that too. But basically x squared minus, I like that the most generally because that's just simple and succinct. But x squared minus x plus 1, its derivative is going to be 2x minus 1. Okay, so at x equals to half, you're going to have a local minima. Okay, it's going to be a global minima actually, because you're going to have a parabola, and at x equals half, it's going to have its apex, and then you're going to have 0, then you're going to have minus 2, then you're going to have minus 1. So you kind of see that clearly the maximum value of this parabola is going to occur at minus 2. Okay, that's intuitive. I would have just rigorously completed the square, but we know that because you're looking at maxima and it's not occurring inside the interval minus 2, 0, it's going to occur at an endpoint. So it's either going to be at minus 2 or 0, and then you can just plug in and figure out which one it should be. So I just plug in, so x equals to minus 2, we're going to get 4 minus of minus 2, which is 6, plus 1 is 7. Okay, so at minus 2, we're going to get 7 for our value, and at 0, we're going to get 1. Okay, so indeed, our maximum value of x squared minus x plus 1 on the interval minus 2, 0 is going to be 7. Okay, so we can ensure that, so I can write that down here just to kind of emphasize that x squared minus x plus 1 is going to have absolute value less than or equal or even less than 7. Less than 7 if the absolute value of x plus 1 is going to be less than 1. Okay, so x is within 1 of negative 1. Okay, x plus 1 is x minus minus 1. So let's now do our epsilon delta proof. Okay, so I just did some intuitive sketches there. We've got this expression here. So let's do our epsilon delta proof and just write it out very precisely. And I hope by now you're getting the hang of this, but the next one, stay till the end, because the next one's going to be very important. It's going to be a slightly different variation where we're going to have to do a different trick to solve our epsilon delta proof, but this is the essence of all of them. And once you've proven a theorem, the limit of the products is the product of the limits, or something like that, or the ratio quotient rule for limits, then you can do that with epsilon delta proofs, and then you can just repeatedly apply to whatever problem, right? So in this kind of thing, you'd have a sum of limits is limit of the sum law proof, and you just have to establish, x cubed is like a product of limits. Okay, so you have the product, sum, and quotient laws for limits. That's all you need. But understanding this is important. Okay, you don't want to just apply it. You want to understand. So I mean, by now at this level, you know that. We have calculators, but you still want to know how to do mental math. It's important to understand the foundations. So let's now get into our proof. So let epsilon greater than 0 be arbitrary. So same idea as before. Let epsilon greater than 0 be arbitrary. Now what do I want to pick delta to be? Okay, so let delta equal to, so again, delta is going to equal to the minimum of 1 comma basically epsilon over 7. Okay, that's going to be our worst case scenario. Okay, because we'll see that again, but our x squared minus x plus 1 is always has absolute value less than 7 if x is in the range of 1 of negative 1. Okay, now I always take 1 because it's just simple. You could take 2, you could take half, it doesn't really matter. People like to take 1. You'll find that, if you read books or notes online, they'll take 1 just for simplicity. 1 is simple. Okay, so we've got that. Now we know that if the absolute value of x minus of minus 1 is going to be less than delta, okay, then we know the absolute value of x cubed plus 1, again, we can say this is going to be the absolute value of x plus 1 times x squared minus x plus 1. Right, times x squared minus x plus 1, and that's going to be, we want that to be less than epsilon. We know that because our delta is the smaller of 1 and epsilon over 7, it's in particular less than or equal to epsilon over 7. Okay, so that's the first step, okay, because we are going to bound this. But first we know the x plus 1 part is going to be less than something to do with epsilon. Okay, so we know this is going to be less than epsilon over 7 times the x squared minus x plus 1, absolute value of that. So just to be clear, actually that expression is going to be positive on our interval minus 2, 0, but it doesn't matter. Just keep the absolute value because that step is next, as long as we have both of these quantities, right? So as long as we have the second one, we got this expression that absolute value x plus 1 is less than epsilon over 7. And now we know that our x is within 1 of negative 1 because our delta is the minimum of 1 and epsilon over 7. So because of that, we know this quantity has a maximum value of 7 on the interval minus 2, 0. So this is going to be equal to, so this is going to be less than 7. So I'll just write that down. You know, it could even be less than or equal to 7. That would still be fine because we already have the inequality here. But, you know, it's a less than 7. So that means that the total expression is going to be less than epsilon. Okay, so there we have it. So again, we've solved the problem. We've found a delta in terms of our epsilon to ensure that no matter how close I wanted x cubed plus 1 to be to 0, you could find how close x had to be to minus 1 to ensure that what I wanted was satisfied. Okay, so we could do it that way. So it's a game we played. And now the last limit we're going to do is going to be super fun, and it's really fun to make this video. I'm actually a little bit tired right now, but I'm loving making this video. I'm going to do one more. I've set out to do 5 limits. So if you're enjoying it and you haven't already, please don't forget to hit the like and subscribe button, and please consider sharing. You know, if you're studying these concepts and you know in university, school, high school, you know, just share it with people. I try to make math fun and accessible, and the more people can benefit from it, the happier it makes me, because I love doing this in my free time. And I think that, you know, if you're enjoying it, then I'm sure there are other people you know who enjoy it as well. And if you share it with them, that would mean the world. So thank you so much for all your support. And I'm going to get to the last limit now. So let's get into that. All right, so we have the last limit now. And this is going to use a slight variation of some of the ideas we've considered, but it's a little bit tricky. I want you to think about it. Okay, if you've worked this far, I hope you've been following along and trying to work out the proofs yourself. So I want you to try to really be creative and play around with this, and then we can do it together. Okay, so if you haven't already, consider pausing the video, working this out, or even pausing at individual steps if you need a kind of push forward. But, you know, really, it's all the same processes. Once you understand the core idea of what you're trying to do with these epsilon delta proofs, it's just the same process repeat. So it's just like muscle memory to get into practicing it. So we're going to get limit x goes to 9 of root x minus 5. Again, when x is exactly 9, because this is a continuous function, and x is 9, you get the square root of 9 minus 5, which is 3 minus 5, which is equal to negative 2. Okay, so that's going to be our limit value, and now we have to rigorously prove it. So I'm just going to steamroll through this. We want the absolute value of root x minus 5, so root x minus 5 minus of negative 2. Okay, so that's going to be plus 2. Okay, so minus of negative 2, I'll just write it in 2 steps. We want this to be, if I give an epsilon, or let's reverse the roles. If you choose an epsilon, so that you want this to be less than epsilon, you want root x minus 5 to be sufficiently close to negative 2, my job is to find a delta, so that if the absolute value of x minus 9 is less than delta, then I can ensure that. Okay, so if x is sufficiently close to 9, I can ensure that. How close? We need to figure that out. So we need to solve for delta as usual in terms of epsilon. So now we can write this. We need to somehow write this expression in terms of x minus 9. Okay, that's going to be slightly tricky, but the same idea as before, but slightly different. So you're going to get root x minus 5 minus 2 is going to be, it's going to be root x minus 3. We want this to be less than epsilon. Okay, now how do I write this in terms of x minus 9? Okay, so that's going to be slightly subtle. Basically, the point is that, you know, you can't really factor an x minus 9 into it. So you have to kind of do what we do with limits if you have like radical limits, which is you want to multiply top and bottom by the conjugate. So here we have root x minus 3. So if you multiply root x minus 3 times root x plus 3, okay? So you do that, okay? And that's the difference to get to x minus 9, okay? We want to get rid of the radical because we want to find an x minus 9 in here. We need to get rid of the radical, and whenever you do that, you know you use the difference of squares formula. So you multiply by the conjugate. Root x minus 3 times root x plus 3 is going to be root x squared, which is x, minus 3 squared, which is 9, okay? So therefore, you know that root x minus 3 is equal to the absolute value of x minus 9 divided by root x plus 3. That's going to be the expression, and we want that expression to be less than epsilon, okay? So how do we ensure that that's less than epsilon? What does delta have to be? So I want you to pause it. If you haven't already done, pause it here and try to work it out, okay? And then we will get to the next step, okay? So I'm just trying to help teach you. I'm not looking for more watch time or anything like that. I just want to help you to learn. And so if you pause it and try to work it out and you're confident with it, I'm really happy. But let's actually just now get to it. So we've got this. So we've got absolute value x minus 9 by root x plus 3. So we know we can make absolute value x minus 9 small. Okay, that's our job, is to find out how small it's got to be. We have that power. We can make it as small as we like. But the root x plus 3 we don't quite know. So we multiply this by 1 over root x plus 3, or the absolute value of that. So we want to say that this is less than epsilon. So if we make x minus 9, so we have the power to make it as small as we like. So same game, let's say that we make x minus 9, absolute value of that to be less than epsilon times the absolute value of root x plus 3. Okay, let's say we do that. Now if we can do that, right? If we do that, then we are ensured this expression is less than epsilon. But the same difficulty applies. This is not right. Okay, I'm always emphasizing this is wrong. But we just have to figure out how to write. Our delta cannot be this. It has to be in terms of only epsilon. Okay, so we need to look at our root x plus 3. All right, so let's kind of try to understand what has to happen here. So if our x is exactly equal to 9, then we would have to take our delta to be 6 times epsilon. Right, if x is exactly 9, you get square root 9 plus 3, which is 3 plus 3, which is 6. So then we'd get a 6 epsilon. Okay, so that's all well and good, but remember we can't really do that because x can be slightly less than 9, slightly more than 9, right? So, but the thing is this, if x is just a little bit less than 9, we need our delta to be smaller. Okay, so imagine our number line, our 9, we go from something to something, okay, some range of 9. Okay, now we know that if x goes to the right of 9, then our root x plus 3 is going to get larger. Okay, so that means that we don't need our delta. 6 epsilon is fine for our delta. Okay, we'll get something higher than 6 times epsilon is what we need. So 6 epsilon will be better than what we need. But if our x goes to the left of 9, then we have an issue. Okay, now I want to make things nice. I don't like taking the square root of 8 or something. So here we're not going to take delta equals to 1. Okay, we can actually, but we're not going to be very precise there and take the precise maximum value of root x plus 3 on the interval from 8 to 10 or something. We're just going to observe, or the precise minimum value of it. Okay, we're just going to observe that root x plus 3, the worst case is say when x is 4, that's the closest perfect square to 9. When x is 4, then basically we get root 4 plus 3, which is 2 plus 3, which is 5. So then we're going to get 5 epsilon. Okay, so let's just take want our delta to be equal to 5 epsilon. So we want it to be less than or equal to 5 epsilon, and we also want it to be small enough that it's within the range of 4 to whatever. Okay, it doesn't matter what we go to the right, but we want our interval to be symmetric, so 4 to 14 or whatever. Okay, so we can just take our delta to be less than or equal to 5 epsilon, and we have the power to make delta as small as we need to ensure our end expression is less than epsilon. So we can take our delta to be less than or equal to the minimum of 5 epsilon and let's say 5. Okay, we could also take 1. It doesn't really matter. We can take 1, 2, 3, 4, 5. We can't take 6 because then we'll get a smaller number than 5, and then we need our delta to be even smaller. So let's take the minimum of 5 and 5 epsilon, and let's then write our proof. And this is just the last one. I'm going to write it out very precisely to really help consolidate it for you. It's been a marathon. It's been fun. I've actually been recording for an hour on this. All right, so let's get into our epsilon delta proof. And here it's kind of going to be looking blind. I'm not going to actually show what we just did. I just erased it. So let's get into it. So let epsilon greater than 0 be arbitrary. And now we want to say that we want to pick our delta. Okay, so let delta equal to the minimum of 5 and 5 epsilon. Okay, it didn't really matter, as we said. It could be minimum of 1 and 5 epsilon, that would have been fine. 4 and 5 epsilon, that would have been fine. So let delta be that. So if the absolute value of, the x minus 9, because we're taking limit as x goes to 9. So if absolute value x minus 9 is less than delta, then we know that the absolute value of this expression, root x minus 5 minus 2, okay, which is going to be root x minus 3. Okay, that's going to equal to the absolute value of x minus 9 divided by the absolute value of root x plus 3. Okay, that's going to be the expression. And x minus 9 by root x plus 3, that's going to be, well, we know that the x minus 9 is less than delta, right? and delta is a minimum of 5 and 5 epsilon. So again, it's the same kind of order. The first step we're going to use to handle the x minus 9, we're going to use the fact it's less than 5 epsilon. So we're going to say that delta is less than or equal to 5 epsilon. Delta is less than or equal to 5 epsilon, but absolute value x minus 9 is less than delta. Okay, so we know that it's going to be less than 5 epsilon. So you get 5 epsilon here. And then secondly, we know that delta is less than or equal to 5 because it's a minimum. And because delta is less than or equal to 5, we know that the minimum value of root x plus 3 on the interval 4 to 14, right? Because we're looking at an interval around 9, x minus 9. So again, I write 4 to 14. We know that root x plus 3 is at least the root 4 plus 3, which is at least 5. So therefore, if you take the reciprocal, it's less than 1 over 5. So we're going to get a 5 on the denominator. That's going to be equal to epsilon. So that's our epsilon delta proof. And yeah, it's been really fun. It's been a marathon. I got my COVID booster recently, so I'm really tired for some reason. I think that's probably the reason. I feel like I'm going to fall asleep, but I love making this video. It was a lot of fun, and I hope you loved it too. And please don't forget to check out a lot of other fun content on my channel you're going to love. Please don't forget to like and subscribe. And again, please consider subscribing on Patreon if you're really enjoying my content. Every little bit helps and makes a huge difference to my channel. And I'm so grateful to all the support. Thanks so much to Alex and Nathan. Here's a fun proof. If you really enjoyed this video and enjoyed learning these analytical ideas, a proof that an increasing function that is monotonic, okay, an increasing function, it's going from R to R, has to be continuous almost everywhere. Okay, it cannot be continuous at discontinuous at a lot of points. Check that out, it's going to pop up on the screen here. And for another fun video you're going to love is a number theory proof. Okay, it's about harmonic numbers. It's connected to the Riemann hypothesis. It's so lovely, you're going to love it. It's a really simple and elegant number theory proof. Check it out, it's going to pop up on the screen here. Wish you an amazing day. I'm super excited to see you in either of those videos. Wish you a great year ahead. Hope you ace all your exams, and I hope this video was really helpful. And if you watched this far, please drop a comment down below. It means so much if someone watched this far and got to the end and saw this whole video, and really if it helped you master epsilon delta proofs. Catch you later, and I wish you all the best.